Good afternoon to everyone, and welcome to this new CONSELF webinar. My name is Alessandro Palmas, and today I'm going to show you how to use CONSELF simulation platform to perform wind tunnel simulations. Before starting, I just want to remember you that if you want to ask a question in the live chat at the end of the presentation, you need to log in with your Google account now. Few words about CONSELF. We are based in Italy. Our headquarters is in Milan, and we are also on different areas in Italy. And we have also a distributors network worldwide that spans from the Far East to the Americas. As you can see here, we schedule a set of webinars that started in April and will continue this month. We already had the 3 webinars on HVAC, valves, and pump simulation. And then next week, there will be a webinar on buildings, and the week after, one webinar on stress analysis. That's, as you can see, it's a new added webinar because we just had the dedicated application to perform this kind of analysis on our web platform. Here you can find also our references. We invite you all to follow us on LinkedIn in order to stay tuned with all our updates. And if you need any kind of information or details, don't hesitate to write us on info@conself.com. This is a brief summary of what we do. Our core business is the development of a simulation platform on the cloud. And on that platform, you can perform fluid dynamic simulation and also structural analysis too. We also offer a cloud computing service for all those companies that may need a computing power on demand to run their software. And we also provide this kind of service. Finally, we are also an engineering consulting company that can help to optimize design of your products, as well as integrate the simulation technology in your design process. Let's focus on what we are gonna see today. And our wind tunnel will be used to test a very nice geometry that you can recognize here in this slide. Is a front wing of a Formula One vehicle. So let's start to focus on why using simulation as a virtual wind tunnel. Well, the first and most intuitive reason is that you can optimize your design. For example, obtain the optimal downforce over drag ratio, maximizing that downforce and minimizing drag. You can also reduce production costs because these tools can be run in the very first design phase, avoiding wrong choices and thus correcting the design in the very first steps. You can explore a wide solution space, meaning that you can test in parallel different designs and find out which one suits best your needs. In this sense, you are basically virtual prototyping your final product and testing it before making any kind of decision in the manufacturing process. At the same time, the advantage of the virtual simulation with respect, for example, of real lab tests is the fact that you can measure the entire environment, your entire fluid domain, in case of CFD simulations, and you can perform this simulation in real scale. Sometimes this is not possible. Maybe for a vehicle it is. For an airplane or for a building, it is almost impossible. Now let's focus on a few key aspects of this webinar. The first thing that can be quite interesting is we will learn how to set different mesh refinement for a single geometry. What I want to say is that even if few boundaries will play the same role from the fluid dynamics point of view, we will divide them in different pieces in order to specify different refinement on your mesh. Referring to the model we are going to use today, as you can see, there are 3 different color zones. And these are the boundaries that we will define in the platform to prescribe different mesh refinement on each of them. As you can see, there is the body, there is a part called wing high refinement, and another one called wing low refinement. The difference is mainly because the wing with high refinement, as you can see, has very small gaps that has to be captured by your mesh. At the same time, the body doesn't play a major role in this simulation, and so the mesh refinement can be maintained quite large. This will optimize the number of elements we are going to divide our computational domain. So this is a very interesting feature that we will see today. Another important aspect that we added with the 2.2 version is the mesh quality evaluation. Before running the CFD, you can plot the mesh quality parameter to find out if your mesh has a lot of cells that are poor in terms of, let's say, aspect ratio, skewness, or orthogonality. And we will see how to do that. About the post-processing, we are going to see the streamlines plot in order to find out the trajectories of the particles entering from the inlet and interacting with your geometry. Finally, I will show you how to estimate the downforce produced by the model using ParaView, an open source tool for scientific data processing you can download on its own website. So let's now pass to the simulation, and I will show you every single phase, starting with the registration and subscription to the free plan. Let's now shift to the browser. Great. So first thing, you go to our website, conself.com. You will reach the homepage, and here you start the registration process by hitting on the login button on the top right corner of the menu. This way you are redirected to the login or registering page, as you can see here, and you can just insert your email and your password, check the control, and then click on register. I already have my account, so I can just log in into the platform. Once you do that, the dashboard of the platform appears. At this point, I already have some subscription, but you will need to go to the store and buy the, let's say, sign up for the free welcome plan. In order to do so, just go to my account page, and then from the menu store, go to buy, choose Cloud Simulation Plans, and sign up for the welcome plan. It will give you 20 free credits every month to try the platform. So let's go back on the dashboard, and that's the very first tab you will see in the platform. It contains few data and graphs like the amount of credits you have and those you spent, the number of steps you launched during your simulation, and a resume of the last 6 simulations with their number of credits. So now we can shift to the simulation tab, where we will start our process to create a new case and setting it. But before doing that, I will just show you the new feature, the new tab called Storage, that allows you to monitor your available space, the storage of every single simulation you have on your account, and here you can delete the old simulation you don't want to have anymore. There are two other features on the left menu bar, and it's the user manual that redirects you to our wiki page, where you can find the manual that guides you through every feature, every settings of our platform. We will use it later in our process. Then there is finally the contact support button, so you can send your inquiries and question to our support. So now let's start with our simulation. As you can see here, we have the first option to select, and is the application we want to run. As you can see, there are a few dedicated applications in this menu, and this is something that we are going to build and enrich every month with every release. Right now, there are 3 specific applications for the oil and gas sector, HVAC and turbo machinery. There is another one for the structural analysis part. We are going to use the CFD general application. So we have just to give a name to our case. Let's call it front wing webinar, and let's create it. Now we are in our case, and this is the process we are going to follow to complete our simulation. As you can see, it shows 5 different steps. The first is geometry. Then we have 2 mesh steps. First one is the mesh 2D that allows us to perform a surface meshing of our geometry. Then the volume mesh in mesh 3D, CFD setup, and then results with the post-processing. In geometry, we can upload our CAD model, clicking on the upload now and choosing the file. I'm going to upload my step file, front wing. We can deal with step, IGES, and STL file. We recommend to use step files because they are the best in terms of accuracy and also flexibility. So this is a step file that is already on our platform now, and a graphical window will appear on the right side showing our model. Few hints on how to interact with the graphical window. With the left button of your mouse and moving around, you can rotate the geometry. In order to pan it, you have to use the center button or left and right together. And if you press the right button and move the mouse up and down, you can zoom in and zoom out. In order to reset the view, you can click on the 2 arrows, and as you can see here, with the mouse left double click, you will reset the center of rotation. So if you want to rotate around this point, you just double click here, and as you can see, you can rotate around that one. Let's now go to the middle of your geometry. Now, another important feature is the information box here. Clicking on it, it will show us the number of elements and the sizes of our geometry. As you can see here, it's the size is reported in the file unit. In this case, we'll see that the X size is around 1.6 thousand. So it appears to be in millimeters. This is important in order to properly set the file units menu here. So millimeters, that's okay for us. We can go to the second step and choose the type of flow. We are going to put our geometry in a wind tunnel, and so that this is an external flow. And choosing external, you have to assign 6 different quantities in order to define our wind tunnel. These quantities has to be assigned, as you can see here, in file units. So we will define our inlet on our minimum Y and our outlet on our maximum Y. So X will be the lateral sides of the wind tunnel, and you have to define here the delta, meaning that here you specify in file units, so millimeters, so 2 meters are 2000 millimeters, to have the side wall 2 meters away on X-min side. Same here on the maximum X. About the Y, we place our inlet 3 meters before the model and the outlet 3 meters away. About the Z, since we have a front wing that is very near to the ground, we define here a gap, a delta of 20 millimeters, so that 2 centimeters will divide the geometry from the ground, and the top of our wind tunnel will be set to 1.5 meters. At this point, we are almost ready. I just want to define the boundaries. As explained during the presentation, we need 3 different mesh refinement on this body in order to optimize solid dimension. And so first of all, I'm gonna define the body that is this. The first boundary I'm gonna create, I have to select every single face I want to add to the boundary. And so this is what I'm doing right now. If you want to, in case there are very small faces, you can shift from the surface plus wireframe to the surface visualization, and this will allow you to highlight very small faces that can be still outside your selection. So this is a process that will be more quick for the remaining boundaries. The first one is always the lengthy one. We're almost there. Okay, so now it seems that everyone has been selected except, okay, you can see here this one is very small. Okay, so now the body seems to be ready. We can create a boundary and just let's call it body. Okay, now I just want to select the remaining faces. So in order to have a better view, I can hide the boundary. I can do it with the selection menu, hide boundaries. Okay, I'm ready to deal only with the wing. So I'm going to select the wing where I want the high refinement. Okay, so every single one of this surface has to be selected. And as you can see, you will see here a particular feature of this model. As you can see here, there is a compenetration problem in the geometry. So the geometry is not perfect. Still, we will be able to mesh it no matter this problem. Here, the same problem too, and we will have the very same thing here, as you can see. So let me say that this simulation has few approximation, and this is the first one, but also the fact that we are neglecting the wheels, the fact that, as you will see, the ground will not be meshed properly in terms of resolution in order to take into account phenomenon that happen in the very near zone in the proximity of the wall. But this is because with all these settings, we will obtain a mesh of around 5.7 million cells. And so you can understand that in order to show you something that is straightforward, I have to make some approximation. So at the moment, I'm finalizing my boundary selection, and we are almost done. Okay. So now we are basically ready. We have just to, as you can see here, there are very small faces near the wing. This one, 2, and 3, and then on the other side, 1, 2, and 3. Okay, we are ready now. This is the wing part with the high refinement. So I just create boundary, wing, high ref. Okay, at this point, you have 2 boundaries. I can hide the one that I just create. And in order to create the final one, I can just select all in the select menu and create it as wing low ref. Okay. At this point, we have completed every single step. I can show every boundary in the complete model. In order to have a summary of our boundaries, you can just click on Manage Boundaries, and here it is. We can see every boundary with the number of faces and all the details. So we are good now, and we can submit our job. Every time you submit a job in every step, you will see it in the casing process section in the simulation tab with the progress bar, the step name, and you will see the progress. Okay, this step will take around a few seconds, but when you will launch CFD simulation, you will see the progress bar growing, and it will give you an idea on how many minutes or hours you are going to wait for it. So, okay, the geometry step has been completed, and as you can see, the case moved forward to the second step that is meshed 3D. You can just upload the previous step. This is a common thing to do in every single step. Starting from the second on, you have to select the step from where you arrive. So here, geometry. You select geometry, and you will see the graphical window loading with your new geometry appearance. And as you can see now, we have both the bounding box and also our model. And if you look here, you will see that our body has been grouped together, and now you can select the whole body with a single click because you have the boundaries grouped. So now let's start with the Mesh 3D settings. On the left side, you have the boundary selection with the select menu. In this menu are contained every single boundary we defined, also with 6 boundaries of the wind tunnel. Now, for every single boundary, we have to specify a resolution of our mesh. When you select a boundary, 2 parameters appear, and these parameters are well described in the manual. Basically, they mean how much you want the triangles to be similar one to the other for a given boundary. And so this means that if you insert here 99.9, you will obtain basically equal triangles in all your boundary. 70 is a good value. It's a good default value. For every single boundary of our model, we can use 1 centimeter. As you can see here, from now on, you will have only international system quantities. And if you take a look at the geometry, now during the geometry step, the model has been scaled. So now every single measure is in meters for the length. So here, 1 centimeter is okay for both body, the wing high refinement, and the wing low refinement. For the bounding box, we can leave the default values. In fact, we have here 0.1 meters, and that's a good value for our boundaries. So we can just submit the job and take a look at the result. So since this case will be quite lengthy, especially in the CFD part, I already run the case, and we will use that one in order to take a look at the result. So let's open it, and as you can see here, I just replicated the Mesh 2D. Once the Mesh 2D is completed, you will be in Mesh 3D phase. Again, let's start from the previous step, that is a Mesh 2D step. Let's open it and take a look at what we obtained during the meshing process. Few seconds, and our surface mesh will appear. Okay, that's it. Taking a look at the information, we will see that for these choices we made, we have 300,000, around 300,000 triangles for this surface mesh. So this is the bounding box. And if I want to take a look inside, I can just hide the external boundaries and go inside the domain. And this is the model meshed on the surface, okay? So now it's time to choose the mesh, the volume mesh algorithm. As you can see, you have 2 different choices, a tetrahedral with boundary layer and a hexahedral algorithm. As you saw in the very first phase, in the geometry phase, the geometry is not perfect. So we need to have a robust algorithm, and so the right choice is the hexahedral one, because it is the algorithm that allows you to treat geometries with problems with a very high success. So now let's define the first parameters involved with the meshing algorithm, that is the mesh size. And for our case, the default value of 0.1 is okay. We can so proceed to the second section, that is the boundary treatment. The boundary treatment plays a different role depending on the algorithm of choice. In case of tetrahedral, you will have the boundary treatment will allow you to set up the boundary layer, basically. But with the choice we made with the hexahedral algorithm, the two values that you have to set that appear when you select the boundary, you see are the wall settings and the first wall cell height, and the layers number and the dimension of the cell. What's the meaning of these parameters? As always, you find the definition of this parameter in the manual. So let's now take a look. You have every single step here explained. And in our case, we want to focus on the hexahedral boundary layer. So two parameters, layer number and wall cell dimension. So, well, the wall cell dimension defines the dimension in the normal direction to the surface that you want your mesh to have for that boundary. The layers number define the number of cells you want to be added before allowing the mesh to be coarsened. So in this case, let's start with the body. As said before, the body needs a cell that can be higher with respect to the other surfaces. So let's define for the body a small cell of 1 centimeter. As layer number, let's use 3. This number will be used also for the wing. Wing with high refinement, again 3 layers, but this time we need a high refinement. So for this boundary, we will use 1 millimeter. Or let's say 2. 2 can be okay. Then let's proceed to the final part of the model, and let's define also for the wing with low refinement 3 layers, and this time 8 millimeters. So you saw that our definition of different boundaries for the very same model geometry allowed us to define 3 different first cell dimensions. And in this case, this will allow us to optimize the mesh and to obtain a good quality with a relatively small amount of cell. For the bounding box, we can leave layers number to equal to 0. This means that the software ignores the setting of the cell dimension and has refinement on the boundaries, the value of the dimension of the triangles defined in Mesh 2D. So if you keep 0, the software doesn't read the number you put here and has refinement for the walls where you set 0, the number you prescribed during Mesh 2D. That is 0.1 in our case. So let's start, and you can just submit at this point. We will see the job starting and completing the Mesh 3D. Once it has been completed, you can just go to the CFD section and load your Mesh 3D. As you will see now, a different graphical window will appear, and this new window allows you to have a better interaction with your mesh, and we will see how in a few minutes. The first thing we will do is to find out how many cells the mesh produced and clicking on the top left button, and then on our file, then clicking on the highlighter here, you will see the data info. And as you can see, this mesh contains around 5.7 million cells. So if we want to take a look inside the mesh, we can just select the file and then click on the plus here and apply a filter. Let's say we want to clip the mesh around in the vicinity of our model. So let's define the origin of our clip in 0.3x. And let's take a look how is the mesh in that zone. So as you can see, we have the clip now, and we can also choose a representation surface with edges. This will show us the cells inside the domain. As you can see, there is a high refinement zone near the wings. We can just hide the menu here and then zoom in. Too much. Okay, as you can see here, we have the wing with the different surfaces and our mesh. So as you can see, the very high refinement we set allowed us to add a proper number of cells between the different surfaces. So finally, I want to show you how to find out if the quality of your mesh is good enough. If you go to just delete the clip, and if you come back to your file, you can color it by mesh quality. Choosing it, you will see that the majority of your mesh will be blue. This meaning that the majority of your mesh is okay. The mesh quality is a cell-based value that is 0 when the mesh is good and 1 when the cell has problems. So one way to highlight where the mesh has problem is to isolate the cells with the mesh quality value equals to 1. In order to do so, you have to apply a filter called threshold. The threshold filter when you specify the range and the variable on which you want the threshold to be applied, isolates all the cells that contains the mesh quality variable inside the threshold range. So now you will see that few spots appear here, and these are the zones where your cell has problem. So how to find out where these cells are located in the domain? You can just highlight again your entire mesh, go to representation and set up a value of opacity lower than 1. This way, as you can see, you can see through your model and find out where the problem is. In this case, it's very near to the rear part of the lower wing. So you can just go back and redefine the mesh refinement in that zone in order to improve your mesh quality. For us and for the purpose of this webinar, this mesh is good enough to proceed. And so we will continue from now on with the CFD. So the CFD is composed by 3 different sections. And the first one deals with fluid and turbulence model. We will be using a simulation where the inlet has a velocity of 50 meters per second. At these velocities, fluid can be considered incompressible. So incompressible is the choice of the fluid model. As turbulence model, we will choose Spalart-Delmaras, that is the simplest one. Density, 1.225, density at 15 degrees Celsius. Then we have to specify the dynamic viscosity. And then we have to initialize our fluid. The pressure, we will use the atmospheric pressure. The velocity, we have the inlet in y minimum, and so the velocity will be aligned to the y-axis. So here we are going to use 50 in the inlet, so now we can use 25 as an initialization. The turbulence can be, the default value is okay. So we can proceed to the next part and set up the boundary condition. For each boundary, we have to prescribe the behavior of the boundary from the fluid dynamics point of view. Let's select body, and the default is the wall no slip. That's okay for the body, as well as for the wing and the other wing. Same thing for the Z axis at the minimum, so the ground is a no slip too. And then we can go to the X-min and X-max are the lateral walls, and we can use the symmetry boundary condition for both. Then there is the Y-min, that is the inlet, and we can just choose Y inlet velocity, 50 meters per second. And this is the hydraulic diameter that is well explained in the manual. And basically, it's needed to define the inlet, the turbulence at the inlet. We can use the 2 meters for our configuration. Then there is the bounding box, epsilon max. That is the outlet. We are going to use pressure outlet with the atmospheric pressure. And finally, we have the Z max. This is the ceiling, basically. And we can assign here, we have a few choices. Maybe we can assign no slip velocity aligned with the flow from the inlet. And so that's it. We can proceed now that all boundary conditions are set. We can proceed to the simulation settings. And here we have to choose between a steady simulation or a transient one. For our case, steady is okay. We have to assign the number of iterations and the output frequency. So how many iterations you want between each save of your solution. So if 500 is okay. Just click submit, and we will see again the case in the simulation running tab of simulation. And once it's completed, you can load your result. In the results section, again, you have to choose the step, and that's the CFD. And the result will be loading into your graphical window. In the meantime, you can take a look at the residuals, and as you can see, after a first not smooth behavior, you have decreasing a curve here of the residuals, meaning that your simulation converged to the right solution. And you can also download results. You will see we will need to download the file in order to post-process it, to find out and evaluate the downforce. So let's start now a few post-processing of our simulation. First thing to do is to move the simulation result time to the last one, so to the conversion iteration. Then we can just let's take a look at pressure and velocity near the wing. So I can just open my menu, select the system, and clip it in the very same place we did it before. So let's choose the here 0.3. And let's now zoom in a little bit. As you can see here, this is the pressure contour, and obviously there is the high pressure that is pushing the wing downwards. We can also take a look at the velocity, and we will see how on the bottom part the velocity is higher than the upper part of the wing. So it's just to have a look at the pressure and velocity distribution. We can also add the entire geometry and to take a look in. You see here the distribution. We can just make it a little bit less. Okay, we can take a look here. Yes, and so this allows us to see the velocity distribution around our wings. And now we can also take a look at the particle trajectories. You can add the string tracer filter to the system file, maintaining the system file, and then selecting the vectors on which you want to integrate the path of the particles. Then selecting the source point. This depends on where you want to see the particles moving. So for our choice, our point of view in the graphical window, these values are okay. You have to do some trial and error here. Then you can just click OK and color it, let's say, with the velocity. So you see, this shows us the interaction of particles flowing around our wing, and also the interaction of the fluid and how it changes the pressure values and the velocity values when interacting with the wing. Okay, now the last thing to do is to perform a calculation of the downforce, an estimation, a rough estimation of the downforce. In order to do so, we will use ParaView. To use ParaView locally, you have to download your results. And so let's go to the ParaView window. Okay, so I will load my state. It's called state. That is basically an elaboration of the results file. And I will show you in a few seconds the result of the downforce calculation. I will also explain to you how to do it. On the left side of the window, you see the tree diagram of Paraview. It starts from the top with the case result. Okay, open phone. This is the result file. On that one, you are going to apply a series of filters, as we did online, to obtain our result. So here is the final image and the final values, but let's now focus on this menu here. So starting with the result file, that is the very first one, you add the first filter, that is extract block. You can obtain it from the menu filters, alphabetical extract block. With extract block, you select body, wing, high ref, and wing low ref, that are our boundaries of the boundaries of our model. Doing so, from the entire domain, you will extract the block composed by the geometry. On this block, you extract the surface, and again, using the filter in the alphabetical menu here, on the surface, you generate the normals, and now, given your pressure distribution on your model and the normals, you can evaluate the force in the direction in direction x, y, and z simply by the calculator operator here, performing pressure, the product with between pressure and normals x, normals y, and normals z. So at this point, you will have then the three forces listed here. And the last thing to do is to integrate your variables, that are basically phase variables, on the entire domain. And once you do so, here there is a plot of the downforce. As you can see, basically every part of the wing produce a downforce in this image. And here you have the values. Let's talk about these three values, force x, y, and z. So x is the lateral direction. As you see, is very small value, is 21 newtons in the minus direction. It should be 0 if a perfect symmetry has been achieved. But you see here the problem of the mesh, and you saw also the problems of the geometry. So obtaining 21 newtons, that are basically 2 kilograms, it's quite a good result with all the simplification we made. The force in the y direction is around 700 newton. Okay, so we have a quite, not so small drag force acting along the y direction, that is acting against our engine, okay, because it's directed against the vehicle. And finally, here you see the force in the z direction, that is minus 2,742 newtons. That is around 274 kilograms in the z direction. Remember that we performed the simulation at 50 meters per second. That is around 180 kilometers per hour velocity. That is basically around 1/2 of the maximum velocity that the Formula One vehicles can reach. So this is quite a meaningful number for this condition. Okay, so that's everything I want to show you today about the post-processing, and we can go back to the slides in order to start the question and answer session. and then we will complete our webinar. Okay, so in this slide, you can see how to ask question in the live chat. And if you have some, I can answer you right now. In the meantime, I invite you to register to our website that you can find on our website, and also to follow us on CONSELF in LinkedIn. We post there all our updates, and we keep you posted about new releases and new features we are gonna add very soon. There will be quite a lot of interesting additions during the next weeks. Also, I invite you all to write us to our email address if you have questions, if you want to know some details, if you want to perform a demo live with us, if you want to try your geometry. We are completely available. And finally, I want to suggest you to use the free plan, to subscribe to the free plan in order to use the platform and try out it with your geometries and cases to test the features. So since there are no questions, I thank you all for your attention, and I invite you to register to the next webinars we are gonna have next week. Again, thank you all, and have a nice day.